have with us Dr. Subrahmanyam Murala from Trinity College, Dublin. So he's going to talk about like diffusion model for computer vision. So before his talk, so I would like to introduce him. So Dr. Subrahmanyam Murala received the BE degree in electrical electronics engineering from Andhra University, Andhra Pradesh, India in 2007. Afterwards, he received his MTech and PhD degree from the Department of Electrical Engineering, Indian Institute of Technology, Roorkee, in 2009 and 2012, respectively. He was a postdoctoral researcher in the Department of Electrical and Computer Engineering at University of Windsor, Windsor on Canada from July 1, 2012 to June 30, 2014. Currently, he is working as an associate professor in the Department of Electrical Engineering, IIT Ropar, Roopnagar, Punjab, India. His major field of interests are image retrieval, computer vision, medical image processing, and object detection. So once again, welcome, Professor. So now talk is over to you.
Yeah, thank you so much for the introduction, Dr. Rakesh, and thank you for inviting me for this particular talk. So, as this main topic of this particular program is like recent trends in computer vision, deep learning technologies, what we are using in the computer vision. So, I am going to talk in today's lecture about the deep diffusion models for computer vision. So, in this deep learning era, for computer vision purpose, so there are several types of algorithms or models have been proposed, and so step by step these are getting explored and even exponentially growing also. So it was started with a simple convolution neural networks. Before that, simple deep neural network. Then after that, convolution neural networks. Then next version will be the it may be a classification problem or it may be a regression problem. After convolution neural networks, people move in the direction in the regression part for the generative adversarial networks. Or even before generative adversarial networks, there are autoencoders and variational autoencoders for data generation purpose or augmentation purpose. So, and there are some issues with autoencoders. Those are getting resolved using generative adversarial networks. After generative adversarial networks, again, research moved in the direction for advancement of transformer models, transformer mechanism. So, which are self-attention mechanisms got started implementing. People have developed these transformer mechanisms, and then even parallel to the transformers, another concepts are developed, that is diffusion models. So it's, I can say these models are the extension of generative adversarial networks. So in today's lecture, I'm going to talk about deep diffusion models for computer vision purpose. To explain all these things, I will be explaining step by step. So it is not even totally different or disjoint from the existing technologies of CNN based deep learning algorithms. This is this next level or advanced version of that. So that's why I'm going to talk step by step here. But I'm spending maybe 5 minutes for autoencoders and another 5 minutes for generative adversarial networks. And after that, I will be spending half an hour around for the diffusion models, so that I can able to give you the connectivity between the state of actual research started and then current state of the art. Current state of the art is diffusion models, and parallelly other type of algorithms are also there. That is neural radiance field. That is actually not exactly applicable for all types of data sets or all types of computer vision problems. This is more or like with neural radiance field. It's a kind of dimension reduction or compressor kind of algorithms that I'm not touching here. Coming to the autoencoders case, before talking about autoencoders, I will just brief about what are these five types of research components. One is supervised learning. I think you guys already know what is called supervised learning. So where when we are training our algorithm with ground truth label, then we call it as a supervised learning. So example for that is any face recognition algorithm or fingerprint recognition algorithm, image classification algorithm, all are comes under the category of supervised learning. So next one is unsupervised learning. So unsupervised learning means where ground truth is there, that is a supervised, and where ground truth is not there, but still you are able to work out for the required target, that is unsupervised learning. So example for unsupervised learning is here is let's say it's a clustering algorithms. So these are clustering algorithms, k-mean clustering, or maybe dimension reduction algorithms like principal component analysis, linear discriminant analysis. So these are all kind of unsupervised learning where you doesn't have label or maybe ground truth with you, but still you need to reach get the target. Like in supervised case, ground truth is there, but even like if in clustering case there is no ground truth. So if you know about the k-mean clustering, there is no ground truth there. You have to give target like how many clusters you want to make for a given data. That is called k-mean clustering. So there are no targets. Based on that, it is a kind of iterative or optimization algorithm. It is happening k-mean clustering, and based on that, it is getting the results. Next one is a semi-supervised, which means in between the supervised and semi-supervised. For example, there is a video of 1,000 frames, and out of the 1,000 frames, let's say first 100 frames are having ground truth, and remaining 900 frames doesn't have any ground truth. So that time I want to utilize the existing labels for the first 100, and I should label the remaining 900. So that is called semi-supervised process. And now coming to the classification means, I think you guys all know about classification. Classification class, it's like a categorization, face recognition, categorization. These are comes under the category of classification. Next one is a regression. Regression means it's into the data generation, where classification case it is saying what class belongs to the input data. Means input data, whatever input sample we are giving, it belongs to which class. That is called classification. But in regression, it is for the data generation. Example for regression problems are like what will be the temperature tomorrow's temperature in Tirupati at 10 a.m. So that is a question. Temperature is a floating point number, and you have to predict the value. It's not a class. You are not predicting any class. You are going to predict a floating point value. So that is the reason we can call it as a regression problem. So even image generation is comes under the category of image regression. So why I'm talking about all these things? So here I'm talking just to connect what our algorithms, what we are going to talk right now, like autoencoders, or comes under which category, whether it comes under the classification category or it comes under regression category. So guys, do you know it comes under which category? Autoencoders comes under the category of classification or regression?
Classification, I guess, sir.
No. Yeah, I'm not able to see your chat so that you can speak. It's a regression problem. Because autoencoders means image generation or image restoration, data generation or data augmentation. This comes under in this category. So there is no classification part in autoencoders. That is the reason we call it as a regression problem. So clear cut summary here is that autoencoders, what we are going to talk in today's lecture, These are regression problems. These are data generation problems, not categorization problems. Okay. So what is called autoencoders? Let me explain. So in the name itself, we are having answer. It is an encoding module is there, definitely. It is an encoder. Encoder, what is the meaning of encoder? Trying to represent the data with less required information. Like I'm having image of 10K by 10K resolution. How many pixels are there? 10 power 4 means 10 power 8 number of pixels into 3 if it is RGB image. That many pixels are there. If I'm having a video with that much resolution, how to store? If I want to store as it is, it will be taking even one image may take 30 to 40 MB. If it is 10K by 10K resolution, even 4K by 4K resolution, it takes 5 to 6 MB. If I am collecting 30 frames per second, just imagine one video of 10 seconds, how much memory it requires. So to address all these things, there are some kind of algorithms like compression algorithms are there, the softwares are there. There it's a concept of encoding is there, and means it is decreasing the required memory storage, and then we will store that, and then when you need it, you decode it and display it. That is the process. So here auto encoders. Yes, please. So this is here auto encoders, means automatic algorithms development is there in this particular process, and then it is encoding automatically. Once it is encoded into the different domain, different space, so definitely decoding is required. Then only you can able to see the data back. Or if you are encoding and then keeping there is no point. So you have to decode it back. So that is the reason these entire autoencoders are into two modules. Module 1 is encoding module and another module is decoding module. So even encoding and decoding modules are being developed are developed using convolution neural networks only. These are all CNN networks only layers we use, and based on that only we develop this. So coming to the applications case, even I already mentioned, if you want to store any video, so that time or image, if you store that image or video in the as it is format, you need a lot of memory. So few GBs, like even 10 seconds means 30 frames per second. It means 300 images are there, frames are there in 10 seconds video. And let's say if it is a 4K by 4K resolution, one frame requires let's say 10 MB. Just for calculation purpose I am telling. So 300 into 10 MB. So that will be 3000 MB, which means 3 GB is required to store one video with a 10 seconds. 10 seconds means nothing. 10 seconds is nothing. That much memory requirement is there. That can be addressed by using, like, I will encode, and in this phase I will be storing it, and then whenever you need it will be working decoding. Even I am giving a lecture right now. So my lecture is coming, my screen you are able to see, my video you are able to see. It is happening in the same manner. So I'm giving lecture in Google Meet, or it may be Zoom Meet also possible, or maybe Microsoft Teams, or different types of platforms are there. So in these platforms, what they are happening, what they are doing, two types of modules are there in each software. I need to have a Google Meet with me software and Google Meet with you. Then only you can join. In case if you are joining in online, so it means that particular software having encoding module as well as decoding module. When I am giving when I am giving lecture, my video is recorded, that video is encoded, and that encoded data is transmitted to your side, and it will be decoded and displaying, or my audio will be regenerated there into your side. So that is called autoencoder case. Like it's like encoding decoding concept. So in data transmission case. So in the same manner, whenever you are talking, it is coming, means like each case encoder and decoder, it is same. If I give you Google Meet link, can you join that link through my Zoom software? It's not possible. Google Meet link using in the Microsoft Teams, is it possible? As of now, it is not possible. Reason is that encoding and decoding modules are totally different in two different platforms. So this is dedicated encoding decodings are there for a specific software, and you have to follow that only. That is the reason. So this data generation, data transmission, data storage, these are all comes under the category of you can say autoencoders case. And here, as I mentioned, X is an input and X dash is an output. And target is that even same image generation is also fine, because like my lecture video is coming to you, and then same content whatever I'm speaking, it is reprojecting at your place, regenerating at your space, reconstructing, and it is displaying to you. So that is also a fine problem. So I can tell further this autoencoders comes under the category of like non-linear principal component analysis. What is called principal component analysis? It is a linear dimension reduction algorithm. But encoder is a comes under the category of non-linear PCA, because I am using convolution neural networks with all means different types of activation functions, different types of normalizations, max pooling or average pooling, like the self-attention mechanisms, many things we can include nowadays. So with all this, it's a complex network and it is a non-linear network. That's why we can call it a dimension reduction. It is working. If I'm giving image size of let's say 4K by 4K resolution, so I can able to reduce this to very less number of pixels. It may be downsampled by 32, and then I can able to use that data for storage or transmission. I can work out. This is comes under the category of autoencoders. So in after autoencoders, so there are issues with the training of autoencoders. That is model convergence. When you are training your algorithm, model convergence may be an issue. To address those problems, and then accuracy for data generation accuracies are also not so good. So there is a improvements requirement. That is the reason researchers developed the algorithm of generative adversarial networks. It was proposed by Ian Goodfellow. Okay, and here it is again nothing new from autoencoders. It is just there will be a small add-on to the autoencoders. That is like they are adding one more layer, one more network on top of the autoencoders case. So I will give you a small example in this. There are students working under me, let's say. So 10 students are working under me, and I have given 10 project to the means one project to each student, which means 10 projects. So I have given 1 month time to work out that project, and based on that I will evaluate the students. Two ways I can work out. One way is that I will just wait for 1 month and I will start evaluating whatever report they are submitting. Another way is that every 1 week I will conduct the meeting 4 times, and then I will try to check how they are working, and based on that I will direct them, like I will try to give suggestions or maybe mentoring them, so that where they are lagging or where they are doing something wrong, I can able to correct. So obviously, if you agree, means definitely you agree that second option is the best option, because to move the research into the good direction faster manner, mentor is required, or supervisor is required in between. So that is the concept added here. Just simple concept of that is added here. And then we can able to improve the accuracy, generation quality. Very drastical improvement happened as compared to autoencoders. So let's say one example, like in these two images, which image is generated by using computer or which image is the actual one. That is a bit difficult to identify. But if you can check these portions, like very fine details are missing in this image, and fine details are good here. In this it is missing, and here it is good. From this I can tell this is a good image, a correct image, means actual image, and this is generated by using your generative adversarial networks or computer. So so we are able to generate the good results, but still they are lagging at the fine details or texture content. That needs to be addressed. That research still it is going on. Okay, so now if I explain what extra terms are added over the autoencoders, that we need to discuss here. This is an autoencoder module which is called generator module. Generator module means I said that data generation only. Image generation is forming. So autoencoder is called generator module, and then on top of that supervisor is a discriminator module. We are adding one supervisor on top of the generator. And supervisor always verify with the real world results, means ground truth images, and then predicted images by generator, which is called student work. And then based on, he will try to direct the student whether student is going proper direction or not. Based on that, based on the output of the discriminator, it says that real or fake. Let's say if I give an image from the real world, it should say real, and if I am giving output from the generator, it should say fake. Fake means generated by the generator. So which means discriminator is very strong and supervisor is having enough knowledge to guide the student. Then he will say that no, you are still lagging in the target, or the data generation is not at par with the ground truth. The discriminator or supervisor says that. So based on that, if it says the fake means supervisor is saying you are not good enough to generate the data, so readjust it. Then back propagation will be performed on this basis, and then with the back propagation on the generator will be improved. When generator is improved and that generator is able to fool the discriminator, means supervisor knowledge is stagnated or maybe at a saturation level, further he is not improving, means for whatever knowledge he has to improve further to discriminate this student performance. So that time supervisor has to read some more content and then it will be improved further. So this is a game between the student and supervisor. Student is always, or generator is always trying to improve the results, and discriminator is always trying to identify the mistakes. This is the work is going in this fashion. Okay, so this is called generative adversarial networks. While training, it works like this manner. First, discriminator should improve the quality, and then when discriminator is improved, after that discriminator weights will be stored, means fixed. Even previously, generator weights are locked here, and discriminator will be improved. And after that, back propagation will be performed for the generator, and then discriminator will be locked. So once this is done for after few more epochs, then both are ready for the competing each other. So student is trying to generate good results and supervisor is trying to identify the mistakes of the student so that quality is improving. So this is going in this fashion. This is a generative adversarial networks. Still there are issues with the generative adversarial network. This is a loss function. I am not touching much here because our main target is diffusion models. So here one is discriminator is a maximization problem because supervisor is always trying to identify the mistakes of the student, and the generator is a minimization problem where he is trying to minimize them. Whatever the mistakes are identified by the supervisor will be rectified or reduced by student, which is called generator. Okay, now coming to the applications, many applications are there with generative adversarial networks, all types of restorations, segmentation problems, data translation, image translation, and all generative AI comes under the category of generative adversarial networks, where generative AI text is input and image generation. So that is like LLM, large language models are using text to image conversion based on your requirement. But here image to image conversion, these are also comes under the category of generative AI, where image is input and generated output is also image. So this also comes under the category of generative AI. This is the state of the art. Current research is trending research is the generative AI. So some more applications like face aging, like how person looks after 60 plus. Maybe person current age is maybe he is 25, but how he looks after 60 plus. So we can able to generate the based on that. So these are all some kind of applications. Now coming to the problems associated with, as problems with autoencoders are being addressed by using generative adversarial networks. Now what are the problems associated with the generative adversarial networks? To address that, diffusion models have been proposed, and diffusion models are also, we can say, diffusion GANs. We can say diffusion concept is applied to the GAN. It means diffusion concept is something different from the generative adversarial networks concepts. So what are these? Guys, do you know any information about this? What is the major difference between diffusion models, and generative adversarial networks. Okay. So if you don't know, let me explain that. First, I will give you the summary, means what exactly the difference. So if you look at the autoencoders, which is nothing but convolution neural networks, and GANs, which is also developed by autoencoder with a convolution neural network. Discriminator is also a classifier kind of thing. So descriptor is a classifier, supervisor. So that is also developed by using convolution neural networks only. So entire architecture is CNN only. Even autoencoders or generative adversarial networks, all are comes under the category of convolution neural networks only. So the ultimate process of generative adversarial networks are before is like edge extractions, feature extraction, texture information understanding, and based on that texture generation or image generation. Everything is happening in that fashion. So all convolution layers are, it may be high pass filter or it may be low pass filter. So or maybe all pass filter, or means in between something is performing band pass filter. So it is trying to boost the edges based on your requirement. It is working in that fashion. Means it's everything. Convolution neural networks works with the edges only. So it is data content generation, content creation is the process. So that time there are necessity. There is a necessity of requirement of lot more architectures. Different types of architectures are required to develop the generative adversarial networks or CNN architectures for specific application. If you go for face recognition, you should not use more number of convolution layers because if face expression itself is less, and if you go for with a very deeper networks, vanishing gradient problem will come and you are not able to get good results. Micro expression recognition, facial expression analysis, this also requires very less number of layers. If you go with more number of layers, your algorithm may not be appropriate, means the results may not it won't be good. So experimentally we verified that. Based on experience with experimental analysis, I am telling that. So in the same manner, so everything is works based on the edge extraction and texture extraction. Are you agreeing with this point or not, guys? Are you agreeing with me? All convolution neural networks or GANs are working based on the texture synthesis, or texture generation, texture extraction, edge extraction. So these are all comes under like high frequency or low frequency required information, data generation part. But researchers thought in different side, in other way of round they have worked out here, that is called diffusion models. So why should I generate the data? Instead of generating the data, I will generate the noise. And then which is present in the image. Let's say if it is a deblurring problem, image is blurred. So there my target is that I need to deblur it. It means my noise is like wherever edges are there, means missing edges are there, their negative edge will be generated. And once you subtract that from the blurred image, automatically it becomes edge addition only. Its noise itself behaves like a content, texture content. So here extraction is instead of content generation, it is generating the noise generation. It is doing the noise generation, and generated noise will be subtracted from the image. So if it is a denoising problem, generate the noise and subtract it. If it is a fog removal, generate the fog which is actually present in the image, and that is nothing but unwanted information, which is nothing but noise. That noise, predicted noise, will be subtracted from the input image so that fog will be removed. Similarly, rain sticks. When rainy image is there, I want to remove the rain. So unwanted information is rain here. So I will try to get the solution to remove the rain. It means predict the rain, which is nothing but noise, subtract from the image, so that I can able to go for rain removal problem. So like that, n number of applications. All types of restorations can be handled using diffusion models. Even segmentation can also be done using diffusion models. All generative AI concepts can be developed using diffusion models. So, but idea is totally opposite. Where generative adversarial networks trying to generate the data, where it is trying to generate the noise so that I can able to subtract it from the input image so that I can able to generate the good quality output. So for generating the data case, I need very good architectures, very different architecture based on the requirement. But here generating noise case means it doesn't require any kind of architecture. Very simple architectures can also be used. That is the advantage. That is the main advantage of diffusion models. But how this research was started? How this research was started? Just example, let's say this is an input image. On this image, I will add some random noise. This is the output. On that again, I will add the random noise. Again and so on. I will go a few iterations, this process. If you see, after few iterations like 1, 2, 3, 4, 5, 6. At 6th iteration, see, your entire image becomes noisy. So this is the data disturbed now. Now from that I will try to reconstruct back. While training, I will try to reconstruct this back image to the, it's like forward process is this one, disturbance, and then reverse process, which is nothing but generative process, where it is generating the noisy to the clean image. So can I explain this one like a two ways? Noisy generation will be encoding part, and reverse denoising process is a decoding part. That is also autoencoder now. This is also an autoencoder, and this autoencoder can be implemented using GAN. And this is a diffusion concept. Then we can say this is a diffusion GAN. So, but difference is only one thing. Here predicting the noise, there it is predicting the content of the image. Here predicting the noise, and through that we are able to get the content prediction. Noise prediction will lead to the development of content generation. So that is the idea here in diffusion models. So it can be like additive noise, like every time it may be multiplicative noise, or it may be additive noise. So every time noise will be generated, and this noise will be, means few iterations are there, let's say t number of iterations, and let's say 100 iterations are there. First iteration, noise generate, add it on the image. On that output, again some generate the noise, give it, add it. Continuously this you are performing 100 times. This is like, it is it is happening on the same image, image output of that, again giving to the next noise addition, and so on. So it is degrading the image for noise process. So that is called forward process. And this noise addition can be maybe in terms of Gaussian, just for understanding purpose I am telling. Later on it is got standardized using, or adjusted using CNN only. Initially, I will use specific standard deviation with some standard deviation and zero mean. I will add some noise, and that I will generate some noise, and I will add the generated noise to the image, and then I will get back, means I will generate the forward pass, which is a disturbed image, disturbed data. So in the reverse, so this is the process. Like I have generated the noise at this point, and then that is added with the previous iteration content, and then I am getting the tth iteration. Then tth iteration, t plus 1 will be adding, means will be generated by using tth iteration content plus generated noise at that point. So and so on. It is iterative process. It is going, keep on increasing. Like this is a input content, and where noise is here, and on that, based on that, resultant content is generating. Here you can say this is image also the case. It may not, diffusion models not only applicable for images, it can be applicable for videos, or it can be applicable for one-dimensional data as well. So audio signals, or it may be in any waveforms also you can work out using diffusion models. So in the backward process, it's like a minimizing problem. Even iterative process also. let's say 100 iterations you did for noise addition, same manner 100 iterations should be done to restore data back. So adding and removing. So you are disturbing by yourself, and remove means reconstructing it back by yourself. So this is the kind of process you are doing. So here, if I'm just explaining because our papers are still in under review with different places. That is the reason I'm not talking with our work. So here, up to this is the theory of diffusion models. Here I'm talking one algorithm that is like restoring vision in adverse weather, like multi-weather data restoration using patch-based denoising diffusion models. So it means noise addition and restoration. Here network case, let's say in the initial case, what it is doing, let's say in the training process, this image is an input. On that, patches are collected, but nowadays we can remove this patches case also. This work is, I think, around 1.5 years or 2 years old now. So now people are going without patches also, where blocking artifacts are coming. Those are because of those blocking artifacts, people are processing direct images only. So here they are using unit architecture because noise removal, noise generation, or noise removal means noise generation and addition, or noise generation and subtraction for the restoration time. So both cases, generation is noise only. So as you are generating the noise, unit architecture is more than enough. It doesn't require any kind of architectures. It's like creative architectures are not required in the noise generation because unit is enough. So that is the reason network generalization is done. That is the advantage of diffusion models as compared to generative adversarial networks. Generative adversarial networks, based on the application, based on the requirement, you have to change the architecture. But here it is not required. So same unit can work for any application. So it is generating the noise here, and this generated noise is added to the input image. So and this iteration 1 is done. Next one is another iteration, and so on, and number of iterations will be done, and then based on that you are getting the totally distorted data, and that distorted data is this one here. And then reverse process is happening on that, and on that reverse process you are regenerating back to the very clean image. Here same image we are not generating, please understand here. So input is a snowy image, and then which is a degraded image, but output is a clean image. So this process we are using for the restoration of snow images or hazy images. So multi-weather data restoration purpose we are using here diffusion models. So here summarize means like a main important point is that there is no need of architecture based developments for noise generation. Simple unit architecture is more than enough to handle the situation. Because we also developed means like same thing in place of unit we have developed. Experimentally we want to verify. Theoretically I am explaining this one. Like unit is means noise generation is means it's a random one only, randomly content generating based on your requirement of input. So that is not an issue. It is easy to generate using any kind of architecture. So that is logically I am explaining, and experimentally also we have replaced with various number of architectures in this, and performance there is no change in the performance. Maybe percentage wise, if PSNR case maybe 0.1 variation at most. Yeah, but in SSM case also even less than 0.1, 0.2 SSM values only it is getting varied. These are all, this problem is there in any deep learning algorithm. Sometimes based on the training it can happen. So there is no much problem. That is the reason architecture is fixed in the diffusion models. That is simply unit. You should not use any architecture if you want to work. If you want to do research in diffusion models, don't concentrate on architecture development, which is totally waste of time. And here these are all the results for various applications for snow. You can say here snow removal, and these are the ground truth. These are the generated by existing methods. So it worked in this manner. These are the good results it is generated. And here also, like you can say, this is a rain removal problem, and it is also getting improved for better results it is providing as compared to other existing methods. Even this is not our method. I'm just comparing
Sir,
here for understanding.
sir, sorry for interruption. Is there
No
any
problem.
other advantage of diffusion models or GANs rather than changing? We don't have to change the architecture. I mean to say it's a task agnostic. It's not a task specific. So is there any other advantage over GANs?
Yeah, because of noise generation, based on that, results wise, it is really amazing good results it is providing as compared to GANs. Because content generation is a problem. Content generation may not be appropriate and your model may not converge sometimes. But noise generation is easy, and because of that, diffusion models are getting converged, and you are able to get amazing results, very good results you are able to get. That is also main advantage. But this I can say link with the same thing only. I can able to link with same content.
So
Results
sir,
wise,
if we
even you can
want,
take any
sir,
application, it can able to provide very good results.
okay, sir, if I have some problem in which I just want to synthesize the images, so should I move from GANs to diffusion? Diffusion may be the better choice.
Yeah, diffusion is the latest now, state of the art. Diffusion is the
Okay,
better thing. Even diffusion can be implemented using GAN concept.
okay, okay,
Diffusion is one autoencoder network, and you keep that in the GAN. Diffusion GAN architecture is also there. You you use
okay,
diffusion models in GAN.
okay, sir. Thank you.
Mm. Okay, so these are all the results, and the results with this current state of the art for this is the diffusion models. But coming to the drawbacks of diffusion models as compared to GAN, you understand, if you use one architecture, let's say unit architecture, but iteration means one time you are processing. Let's say if I'm using unit architecture for GAN case, simple GAN case, and I'm going for some noise removal, or let's say any kind of data generation purpose. It may be segmentation, or it may be denoising, or it may be restoration, low light image enhancement, anything. So there, one time processing, let's say unit requires a half second or 1 milliseconds processing. Let's say 1 millisecond is required to process input image size of 256 by 256, let's say. So GAN requires that much second only, one millisecond. But diffusion model means if you are going for 100 iterations, the same model needs to be executed 100 times. It means it's not of 1 millisecond, it is 100 milliseconds. And sometimes you may need more than that. That is the reason diffusion models at this moment is not deployable for the commercial applications. But research wise, it is good. So research started. Even transformer mechanism is also like that. Transformers deployment is a bit difficult for the real world application or commercial application, but slowly people are working in the direction of reducing the transformer capabilities. Like capability is always trying to maintain the same, but what is that? Number of parameters and computational complexity have people are trying to reduce it. Same thing, diffusion models are also super duper, it means over expensive for the computationally, so it is too tough to execute in the real world applications at this moment. But research definitely moving in the direction to address all these things. Maybe your hardware capabilities may be increasing, at the same time some kind of solutions may be developed in the diffusion models to address your problems, like these deployment problems. Even at starting of CNN also, it is very difficult to deploy in the commercial applications. But now we are using CNN models in the mobile apps itself. It can able to provide very good results in milliseconds duration. We are able to process 30 frames per second, at least 20 frames per second with a resolution of 512 by 512. So same thing, it can be improved in future as researches keep on increasing, improving. So exponentially it is growing. So even this paper is 2 years old, but now most of people are working in diffusion models, and even results are also getting good. So even it can also be saturated, and people may move into some other direction also from diffusion models. So it can done. It can be
Sir,
like
can we combine diffusion to the transformers to improve their generalization power? Can
diffusion
it
with
be help transformers?
Yeah, you can do that. But
I
one thing,
particularly, sir,
I don't think so. Transformers are not advisable to go with diffusion models. Reason is that I told you, na, there is
particularly
no
when I am talking,
requirement of architecture.
sir, particularly when I am talking about vision transformers.
Mm.
Sir,
There
can
is
we
no use of
combine?
adding transformers in diffusion.
Okay.
Reason is that transformers are expensive, but I said the diffusion doesn't require any architecture. Diffusion case, unit is enough. Performance is same. Even I am telling you, swing transform is a transformer block, means like that architecture. We have replaced, means we replaced the unit by using swing transform, and we experimented for underwater analysis or even underwater image enhancement, haze removal or fog removal case. But performance, but our same performance is coming. There is no modification. Maybe plus or minus half here and there. That is training performance, training variations only. But there is no use. So linking transformers with diffusion, it's not a good idea.
Okay, sir.
But to try to work in the transformers with different types of architecture, different types of mechanisms in attention mechanisms in the transformers, we can work out. But in diffusion, adding transform is not a good idea. So if you are having any questions, I can take up.
So thank you, Murala sir. So as usual, your talk is always informative and awesome. So yeah, so
I think there are
participants.
some questions, Rakesh
Yes,
ji.
yes.
So here sometimes LoRa don't work good on diffusion based phase synthesis network. Even after a few epochs, the model stops generating. Yeah, these are all sometimes, even I'm not telling diffusion models are solving everything. Diffusion model, relatively I'm telling, like if you talk about, let me stop presenting. So if you talk about autoencoders, simple CNNs are enough. But CNN's convergence is not going good. That is the reason we went for autoencoders. And then on top of that, we added, autoencoders are enough, but still there are something lagging in the autoencoder that got addressed by using generative adversarial networks. And on top of that, even there are some issues with GANs, like attention mechanism was not proposed in the GANs. Now attention mechanism is also introduced using transformers. Even before that, squeeze and excitation blocks were proposed. And after that, that is called self-attention mechanism. And on top of that, multi-head attention, non-linear attention. Non-linear attention is nothing but, you can say, it is globally how object is representing and where it is importance you need to keep while training the algorithm or even for testing. So that is called non-local attention mechanism, and even that is further extended to transformers. That era is something bit different path. But here again, GAN case, another route, that is wherever GANs are getting failed. So that able to generate using generalization possibility done using diffusion models. And even still diffusion models may not be good in some results. It may be because of your training capabilities, or maybe initial random weights generation, or something problem is there in the training. You try to work out on all these things. Shravanti?
Shavanti, you have raised your hand, so you would like to ask question. So here, any other? No. So I think no more questions, sir. So thank you very much, sir, once again. So
Thank you so much, Rakesh ji, for inviting me for this presentation.